Hello, everyone. Welcome to our webinar, Cloud Identification on Mars. I'm Julie Hong, a sophomore from Wellesley High School and a student volunteer, and I'll be your moderator for today. This event will be recorded and will be available online after our webinar. Please the presentation, and if you have any questions, feel free to time. Our speaker today is Sebastian Mengwall, a first-year student at Yale. Research in high school with Dr. Scott Guzwich, a research astrophysicist at the NASA Goddard Space Flight Center, and is now working with Dr. Michael Battaglio, a research scientist at Yale in the Department of Earth and Planetary Sciences, on using semantic segmentation to now identify the dust storms on Mars. We're excited to hear about your most recent paper, Sebastian. So,
thank you. Let me share my screen. So yes, hi, I'm Sebastian, and I'll be presenting my research on using deep learning to identify clouds in Mars daily global maps. Framework that identifies Martian clouds and images. It performs at 98% accuracy and speeds existing manual and semi-automatic techniques that are used today. After developing the tool, I generated data 100 images across 6 of the Martian years, and I have used on the Martian atmosphere. I first found my mentor, Dr. Scott Guzwich, at the NASA Goddard Space Flight Center through a cold email during the first months of the pandemic. And he was very generous to add me on to his team. When I first started working with him, I was actually looking at atmospheric data to try to find signals to predict the onset of these global Martian dust storms. And then in June of 2021, he told me about how useful making an automated tool to actually create this data would be. Very tedious and very time-consuming task for all of these researchers. So he thought maybe a machine learning model could be a potential solution. And what I'll be presenting today is the research that and the results that we found out from that. So yes, this is my paper, Cloud Identification in Mars Daily Global Maps with Deep Learning. So just a quick overview of clouds on Mars. There are mainly two different types of clouds. We have water ice clouds and carbon dioxide ice. We will find tropical cloud belt, which is in the tropical regions, which we see here, just towards the equator. But there also does exist in the summer months of Mars, which are clouds made of carbon dioxide ice, which can be found towards the polar caps, which we're actually seeing on the right here. This is the Curiosity rover looking up at the sky, seeing some of these clouds. What's also interesting to look at is how dust storms interact with different types of clouds, but that is for further research. So what we're trying to do with this is that if we can understand clouds better, it will help us in developing better climate models. And this is also helpful for future Mars missions by rovers or even humans, because we can plan ideal mission locations and warn of incoming storms. And here's the data set that we'll be using. These are called Mars Daily Global Map images, MDGMs. These are images captured by the Mars Color Imager, which is an instrument aboard the Mars Reconnaissance Orbiter. This instrument takes swaths of data, roughly 12 swaths every day, that goes around in an elliptic orbit around Mars, and it captures images and stitches them together into an image as shown on the right. This gives us actually great spatial and temporal coverage. As you can see, it has a 0.1 degree spatial resolution. So this is a high resolution to compare to other techniques that we have in use today. It's also great because we already have 6 Martian years worth of data, years worth of data, and it's also still active in use. So we are still collecting data each day about Mars. So in 2021, my mentor proposed this as a challenge to me, as this automated tool would be helpful just for him and the rest of the field to be able to accelerate the research. But when we have this data, what would it be used for? It could be used for Martian climatology research. It would also be important to look at how accurate or how reliable our global climate models are relative to past historical results. So we can use this information to test and train global climate models. And we can also just want to show that there is a potential application for machine learning and deep learning in planetary science, which has not been very much explored over the recent years. Oh, sorry. So this is our general research objective. The challenge that we have today is extracted through manual and semi-automated processes, which is time consuming. And it also therefore limits the spatial and temporal cloud coverage because we cannot spend enough time to get very detailed or very large amounts of data that we can analyze. So the goal is that if we can show that we can use convolutional neural networks to successfully extract information from these cloud masks, it would dramatically create a large amount of data that we could look at, and this would also minimize human input and human error potentially. Okay. So this is the machine learning model that we'll be using, and I'll describe briefly. This is a U-Net structure. A U-Net is a type of convolutional neural network. Convolutional neural networks are types of machine learning networks that specialize well in looking at images and analyzing such images, whether that is what is this type of image? Is it a dog or a cat? But what we're using it for is actually figuring out where clouds are, pixel by pixel resolution. This is a type of deep learning, and a U-Net is a type of convolutional neural network that has multiple different layers, depths, and widths that we'll go into. That makes it a very powerful tool. I coded my U-Net in Python, used the TensorFlow and Keras packages for forward and back propagation during training and whatnot to make it a streamlined process. And I also created a pre and post-processing pipeline, which means I can take a Mars daily global map image, segment it into any way that's the data format that's necessary for the U-Net. Then I take the extracted outputs from the U-Net and stitch it back into a format. So here's a quick overview of what the U-Net actually does. So we can start with a very small square image of 668 by 668 pixels. And just for reference, each Mars daily global map is 3600 by 1801. If you remember, that's 0.1 degree spatial resolution. So these are just a small subset, a little subdivision of what the actual Mars daily global map is. And then it gets fed through multiple of these layers. And the general idea of this model is we have encoder and decoder paths. So first, we go down this left side where it goes through multiple types of croppings, convolutions, max pooling operations. And this encodes features. So we'll be able to figure out whatever the model decides, what is a valuable feature, whether that is the amount of clouds or certain types of colors. And in this very low phase right here, where we only have 36 or 34 pixels per square, we will have the model will try to figure out general information about the characteristics of the image. And then we have our decoder path, which is on the right, as we see going up here, which means that we can figure out how to take our features that we back into a native resolution that we have. As you see, we're going from 34 pixels all the way back up to 484. This means we can get, as you see, an example input and output, something like this, and we can turn it into a cloud mask. Just for the rest of this presentation, a cloud mask is what I'm describing as just a binary filter, which describes if there's a cloud at a given position. So we can see here, this cloud mask says that, oh, I apologize. At these pixels where I'm labeling 1, there is a cloud. At these pixels where I'm labeling 0, there is not a cloud. And then we also have this black region, which we're labeling as -999, which is just like a null value, which says we do not have sufficient information to determine whether there is or whether there isn't a cloud. And if you can see, this corresponds to this black region over here. So we won't be, as in, we just don't have enough information to figure out if there's a cloud. So here's a little bit more about the pre and post-processing pipeline that I've created. The first thing that we have to do is to figure out the polar extents. This is important because we're mainly focusing on the tropical cloud belt, if you remember. These are the water ice clouds within the tropical region. So we would like to remove any excess information that we wouldn't be using. So that is removing the polar ice caps. These two equations, which I borrowed and adapted for this research, give a general overview of how, if you look at the latitudes, and solar longitude is just a measure of time. Over time, winter progresses. So you see like, oh, over time, in the summer months, the southern region or the northern region gets abnormally large. So we have to be able to cut off that polar region so it does not influence the rest of our data. And the second part that we try to do is a smooth tiling process. As I showed in the previous slide, we cannot feed in an entire image into one of these models. We have to subdivide it into smaller pieces that will then be processed by the model, and then we can extract the information from the output and turn it into a whole image. So we have a smooth tiling process that I've created to subdivide these properly. As you can see, we have to stitch together over 50 of these outputs to create one single image. And here's a good visual representation of actually what's happening. We have a breakdown of the pre and post-processing pipeline. So first, we have in A right here, a full Mars daily global map image. This would be an example image. As you can see, this is a subphase G03, day 15. So we can see here that there does seem to exist some clouds around the Tharsis region, which is a very mountainous plateau in Mars. And we also have some activity in the Hellas Basin, as well as some over here. These would be, which we would try to, is classify as clouds. So in step B, what we would do is we would first, as we see here, there's a lower limit of, we would try to remove that type of data. This is like carbon dioxide ice clouds from the information. So we're going to have a upper limit of right around here and a lower limit of right around here of the data that we would feed into the model. And these squares represent a sample subdivision that would be fed into the unit. As you can see, they're a lot smaller than the entire image. So we try to do certain amounts of overlapping so that we can try to get multiple different readings from the model at every given pixel. So we can figure out, we don't have like biased fringes outputs because potentially, usually these models do well when there's a lot of context around it. So it's nice to have a lot of pixel information around a given pixel. But let's say if you're on the corner, on the very edge, you do have a lot of information that's missing. So we would try to figure out from other stitches if there's better information that we can use. That's what gives us to part C right here, which is the greatest weight. So we weight each individual pixel based on how close it is to the center. As I just said, the center is where we'll likely get the best results compared to the edges. So this would give us, if we apply this weight filtering, this would give us the most useful pixels to use for a given area. And then after we have all that information, we fed it through the model, we see what the output is, we get D, which is the stitched final result. As you can see, we have these, the polarized caps are cut off, but we do have these green regions which correspond to clouds, this bluish region which corresponds to non-existent clouds, and this purple is the -999. So this would be a result from the model. And as you can see, it does correspond quite well. I did have to train multiple variants of this model to determine the highest performing one. I collected and monitored multiple variables, specifically loss, area under the curve, F-score, accuracy, and the Jaccard index, which is also called intersection over union. So just briefly, the loss is the variable that we're trying to minimize during training. And for this training, we used a weighted binary cross entropy function. And for the area under the curve, which is also just the area under the ROC curve, which you'll see on the next slide, which is another statistic. We have F-score, which is a value derived from the precision recall curve, which I'll also show on the next slide. Accuracy is just a measure of how many percent correct predictions are we doing. And the Jaccard index is intersection over union. So it measures the amount of overlap that we have between our clouds and the target dataset's clouds. And we try to get this as close to 1. As we can see here, I tried a naive model, which was just setting everything to no cloud, just a complete 0 mask. 4 widths, 8 width, 16 width, 32 width, essentially how many parameters we're trying to train. For these types of models, we are training millions of parameters. And the training data is nearly 180,000 individual subdivisions of these Mars daily global maps, which we augment in certain ways to make it harder to train and to make the model more robust instead of picking up on very small, insignificant features. And we use these with another cloud mask pair from the target data set so we compare and evaluate it using the loss function. Here are the two curves that I was just describing. We are going to be looking at the training and evaluating the model using the ROC and precision recall curves. So briefly, ROC, which is called the receiver operating characteristic curves, are something that we use to figure out about look at the ratio of false positives to true positives that we're actually classifying. Without going into too much detail, what this curve shows is that if we try to tune our model, what I mean by tuning is that we have a threshold value. If you what the model gives out is just a float from 0 to 1 for a given pixel. And what the decision of the threshold is saying, if I see a value of, let's say, 0.5, if it's 0.5 or greater, I'll call that a cloud. And if it's less than 0.5, I'll say there's not a cloud there. But you can change that threshold value of 0.5. So what this part of the research tries to figure out is what is the optimal threshold that we should be using for each of these models. And that is what we're using with this precision recall curve and the ROC curves. And using these 5 different tests, we can see, especially with the zoom in on this top left corner, we can see this green, this 8-width model does surpass a lot of the other models in its performance. So this is why we decided to use the 8-width model as our final results. And the AUC, if you remember from the last slide, was the area under the curve. That is essentially taking the integral of all this space right over here. That's why the 8-width model got the most. The F-score is the harmonic mean of the precision and the recall, which means essentially who has the highest area under the curve for this one. So the harmonic mean is we're trying to optimize both the precision and the recall. Precision is essentially if you take all of the positives, all of the clouds that the model found, what percentage of those were actually clouds? That is what precision is. So if it's 100% precision, then we're saying every single cloud that we found was actually a cloud. But if there's very low precision, that means I accidentally identified a lot of clouds that we mislabeled. That means they were really, false, but we made them, this is a false positive. And recall, which is the proportion of true positives over all positives labeled by the training data. So recall is looking at, of all the clouds that were in the training data, how many did we actually find? So we are trying to also optimize both of those values. And again, in this, we can see 8-width surpasses over here the other models. So now we can also just take a look at how this model actually performs in the real world. After I figured out the best variant, I ran the model on these Mars daily global maps for 6 years. The training data was only around for 1. So this immediately means we have a 5 to 6 times increase in the amount of data that we used to never have. And this is great for researchers because this means we have a large training data set for future models, but it also means we just have a great data set for doing climatology analysis. As we can see in these 2 examples, we are able to successfully capture fine features. And so we can highlight curves and striations, as we can see over here, especially these wispy portions. We are able to detect some of these wispier areas. And we can also see, because of these high detailed fine places that we find, we can use these cloud masks for now local and precise global analyses that we previously weren't able to do. We can also now just compare what our cloud masks look like compared with the target data set that we tried to train against. And what we can see is that our model has finer features and smoother edges. And although we do report sometimes slightly greater cloud extents, we do deem them after analysis to be accurate and not exaggerated. So here's one example of a subdivision of a Mars daily global map image. And this is what our training data said. The target cloud mask, which was manually and semi-automatically created by Helen Wong and Gonzalo Gonzalez-Abad from Harvard CFA. And this was created in 2021. So they did this for 1 Martian year worth of data, which we are grateful for because we used it to train our model. This is what our model outputted. As you can see, these edges are a lot smoother. And as we look at the overlap, we do have a very large amount of overlap, which is very good. But as you can see, there are some small areas where maybe our model only reports, or where there are target only reports. And these are some things that the optimizations of the model are only as good as how the human created the data. So let's look at a few more examples. We'll show 5 examples, 3 on this slide, 2 in the next. Here is again a very cloudy subdivision where we have the training data identifying a lot of the subdivision as clouds, and we are similarly identifying a lot of the region. Here is an area where it's not. If you notice, there does need to be what our model is picking up, a significant cloud piece of information. But what is this actually? In the training data, this was actually nullified. This was said -999, do not look at this. And this was because Wong and Gonzalez-Abad right here. And this image artifact, which our model is sometimes picking up is incorrectly cloud. Part says is that our model is not bug-free. There are sometimes image artifacts that will get accidentally misclassified as a cloud, for example, right here. But importantly, we a pretty much guaranteed cloud that wasn't existent in the previous research. Essentially like a control. There is no cloud whatsoever, and all of us identified no cloud. Indeed, this is a very little cloudy region. Disagreement about the extent of the cloud, but is some, and of course underrepresentations. As you can see, there's some red that the training data picked up, but the model didn't. Oh. And what's super cool about all these data points that we have now is we can start averaging them and looking them over different timescales. So we can look at the cloud frequency evolution over time using these cloud masks. So for this part of the research, we looked at the tropical cloud belt activity. So we were looking at how clouds change throughout the year in Mars. From this research, we're looking at the mean cloud mask cover. This is essentially at a given latitude, what percentage of the time do we find a cloud? And for this research, we found, so solar longitude is just a measure of time throughout Mars, where 0 is spring equinox, and it goes from 0 to 360, essentially just following Mars's orbit around the sun. So this just gives us a measure of time throughout the year. So what this says is that we are seeing around the summer solstice a big growing cloud belt activity in the slightly northern tropical cloud belt, from 0 to 30 degrees latitude north. And this is quickly diminished around 135 to 145 degrees solar longitude. And yeah, as we can see, it's mostly active between 10 degrees south and 30 degrees north. And what is nice is that this agrees with previous published research about these types of trends. We can also look at these monthly. So what we did here is we looked at for specific subphases, which are just essentially months on Mars, what type of activity are we seeing at certain locations? So what this is we're taking 30 or something cloud masks for each month and looking at how frequent are clouds at certain locations. So we can see here mean cloud mask cover during this month is extremely active in the Hallis Basin, the Tharsis Mons. We have Olympus Mons here, as well as some activity in the Arcadia Peninsula that we can also see it in different months. So like this would be like a spring, summer area, and we can see in different areas, we can see different types of activity. Here's another visualization of how we can compare these frequencies with so the averages of the cloud masks that we just shown, we did the same exact statistics with our training data. And so what we could do is we could compare, are our frequencies similar? More than just are we identifying a cloud or not, are our frequencies very similar? And so what we're showing on this plot is we're saying for certain regions where the training data showed 0 to 1 in frequency, at that same location, did we show a similar frequency? And so the ideal would be a slope of 1, perfectly straight line from 0, 0 to 1, 1. And there is a pretty strong correlation that we show in our model. There does seem to be evidence of slightly greater cloud extents, as this region right here in the lower areas is slightly darker than the under region. But this is perhaps something that this is just the slight bias of the model that could be adjusted if necessary. And beyond just using these cloud masks, we can actually look at how these cloud masks compare to other data sets. This one, we're looking at the LMD Mars Climate Database. So the Mars Climate Database is a database that uses information and models to identify, for this, what type of water ice column densities. So essentially how much water ice or how dense are the clouds at a certain region. So what we try to figure out is whether there was a correlation between my cloud masks and the MCD's Mars Climate Database. And so what we can see here is a pretty strong correlation at certain different latitudes, where over time, where we're identifying not. There, if you notice, there is some abnormal spike around 30 degrees north on this one area where there is a spike in the MCD's model that was not identified by our model. And after identification, well, what this actually was, this is actually a location that was cut off by our polar extents. And this is just something that potentially influenced by polar ice caps or these polar hoods could have pushed some of these clouds down that we couldn't see in the simulation because we're looking at real world data. But in an overall perspective, we can see a pretty strong correlation, which is nice. In further research using the LMD Mars Climate Database, we were also able to find a correlation. We were looking right here just specifically at these most active months, these summer months of Mars, and we're trying to find whether there's a correlation at these peak activities. And we can see here where the water, and we're looking at right here, just to give a quick overview, the top is these cloud mask cover frequencies that I found from my model. And this is the water ice column values, so the cloud densities, which are given by this model. And again, this is a hypothetical scenario. This is real world data. So there could be some differences that we're seeing just because we're not basing it on exactly the same scenario. So as we can see here, this is the Hellas Basin. The Hellas Basin has very dense clouds in the simulation, and we're picking up similar things in the real world. And we are also seeing that there's some fainter clouds around the Tharsis region and through this Planitia that are being identified as clouds in our model. Therefore, we are showing that our model is detecting optically thin clouds, which is a valuable thing to know. So in summary, I have designed a deep learning framework that identifies Martian clouds. This can replace the existing manual and semi-automatic techniques and hopefully at least accelerate their processes when trying to research and classify these models. The clouds are identified at 98% accuracy with high resolution and high speeds. We can use these cloud masks to better understand Martian climatology, and we can actually potentially assimilate some of these types of models and this data into existing climate models, which could get us a better understanding of cloud progression throughout the time. Some future work, which I'm actually currently working on, which would be looking at dust storms using similar ideas, but it could also be interesting to look at carbon dioxide ice clouds as well. And what is nice is that this model and data are currently open sourced. You can see them on GitHub, you can fork it, you can run it yourself, you can see that this works.
All right, thank you so much, Sebastian. And oh,
I just
sorry,
wanted
I
to
thought
say a
you were
quick thank
done.
you to
I'm sorry.
my
I
mentor,
apologize.
Dr. Guzwich, and who I'm currently researching with, Dr. Batalio, and also Helen Wong and Gonzalo Gonzalez Abad from Harvard CFA that generated the training data, which made this process a lot more straightforward. So thank you. Yes, I'm totally open to whatever questions you have.
All right, thank you, Sebastian, and thank you everyone for entering such great questions. And if you have any additional questions, feel free to leave them into the chat. All right, let's begin with this one about your model.
Mhm.
Why does the model have a size limit for the images?
Yes, that's a good question. So I think the easiest way to explain it is to look at this image right here. Um, if you look at what's actually happening in each step, you're slightly decreasing your model size every single time. And so eventually there are some times where you could get to, I mean, this is important. We have these divisions by 2. So we'll go from a 328 to a 164. This means that in every single one of these steps, we cannot have an odd sized model. So importantly, you have to pick a very specific type of size of your image so that you cannot end up with an odd size. There are ways to get around this potentially by compression or different size limitations. But for the sake of this research, we had to figure out what is the optimal size that would give us this nice property, but also allow us to stitch together our images in a really nice way. And after doing some analysis, we figured out that this pair of going from 668 down to 484 at the end gave us the best amount of overlap that we wanted. In future revisions of this model, we're trying to figure out if we can use a UNet with arbitrary size, but this is something that would have to do for further research on. But good question, thanks.
All right. What types of filters are used to pre-processing images, and how do we know that they're the best filters for this purpose?
Of this model, here are a few that we're doing to the pre-processing step. This is mainly human generated. So for example, looking at trying to remove the polar extents, for example, pre-existing research. So we're relying on the knowledge of scientists to figure out whether we should be or should not be looking at certain pixels. But during the model, we tried out various different small plugins like a rectified linear unit, a ReLU, or a batch normalization to help train and more performant. But over time, there are some standards that you try to use, like ReLU's batch norms. And this type of framework is quite standard. So this has been tested by other people. There are papers on research on what is the best way to set up your unit. So this is why we went with our current model.
All right. Why did you choose to use UNet instead of ResNet, UNet++, or VNet?
Yes, so there are multiple different types of models that could do a similar idea of taking an image and converting it into a representation of a cloud mask. We tried multiple different types, actually. I tried a ResNet and a UNet++, but what actually gave the best results at the end was a UNet, and so that's why we went with a UNet.
All right. Some people would like to know code. Could you maybe share some more details, because I need to try some similar code and further research in this area.
Great. Yeah. So this code is open sourced on GitHub. If you go to the paper, which is published in Icarus over the past few months, it is available. Also, all training data is replicable. All current data that we generated from this model is publicly available. So if you have questions about what the code is actually doing, feel free to reach out to me. I am updating my model currently because I'm using it for a more advanced type of model. But generally, what the code structure will be is that I have a certain file that just identifies what the other files that do pre-processing steps, prediction steps, analyzation steps. So it's outlined in the documentation if you want to look at it. And yeah, again, if you have any questions, feel free to reach out.
Is there a way to correlate the location of the cloud masks with the temperature changes on the surface of Mars? They're wondering if there are any chances to discover factors impacting cloud masks via this research.
Yeah, so that is important to look at. Clouds are very dependent on temperature. And we can see that there's different cloud activities over the day and night because of the vast temperature differences. For what one limitation of the Mars Daily Global Map is that we only get data around 2 to 3 p.m. So we don't get information from other times of day. You would have to use a different type of model, what I mean by model is like data structure, so that we can get different times of day. That is something that we are trying to look at, like temporal variation, intraday. But with the current tools, it's very difficult without another satellite.
How did you learn deep learning in high school?
Yeah, so that was mainly self-taught. I mean, there's no class in my high school that actually taught it. I used a lot of online resources. There's great documentation online. There's good, I have a few resources if you want them. Also, there's great papers that identify, and what's super nice about machine learning in its current state is very open source. So if you have questions, you can usually find the model or the paper behind that model that can explain to you how that model works. So I mainly just learned by reading a lot. I did take one MOOC, which was just like a crash course into like using astrophysics research with Python. But mainly the machine learning part was
Is your research for dust storms that you're working on now similar to this research that you're doing with these clouds?
Yeah, I can go into a little bit more detail about my current research. So yes, my current research I am doing with Dr. Battaglio, who is a researcher currently at Yale in the Earth and Planetary Sciences department. What we are doing there is we're trying to apply, similar techniques that we identified in this paper to a similar problem using dust. The issue with dust, however, is that the abilities of using a unit is that we can actually visibly see, I mean, as you can see here, we can visibly see the clouds. However, dust, which is the same color as the ground, they're both orange, it's very difficult to figure out where the dust storms actually are just with like a still image sometimes. So the ideas would be to take a similar strategy of using a unit, but try to incorporate more different types of data. So for example, it is actually pretty easy to figure out where a dust storm is by looking at simultaneous images. So if you can see that there's a dust storm in day 1, and then you see the dust storm move in day 2 and continue to move in day 3, if you can use those 3 images together, you can try to figure out where the dust storm is moving. And that means you can also figure out where the dust storm was in each individual day. So with this current research, what we're potentially going to try to do is we're going to try to use transformers, which are a very popular hot topic right now, especially with like ChatGPT and GPT-4, which use transformers for text-based. What we would try to use is transformers to remember previous days. So that is a strategy where we could actually add in multiple days worth of information using an MDGM, same model, same day, but we could try to add context about different days, so we can figure out where the model is. Where the dust storm is.
What does your research?
This is currently active in research. So these models and these ideas are totally going to change and evolve and improve, but that's where my current thinking is.
What does your research and this model mean for future research and projects regarding Mars?
So I hope this research shows that other places that are interested in using machine learning to accelerate their potentially data labeling processes, it can really make a difference. If you can train a good subset of information, if you can get a good model that complements it, it will make it a lot faster to do your research. In addition, it could be important to actually try in future years to understand the climate of Mars using or in assistance with models. So like what I'm doing here is I'm converting existing knowledge about Mars into readable formats by humans. But these climate models that we're trying to compare against are mainly human driven. So maybe it'd be cool or novel to try to incorporate some of this black box math of a machine learning model into the climate models themselves. There is some difficulties in trying to do that. Some scientists may not be ready to actually take such a step. But it is potentially what the future could hold, especially if models get more complicated and more computationally intense.
Is it possible to understand deep learning architecture without studying advanced math?
I think so. I started using it. I mean, I had a new linear algebra beforehand, but I think you can understand machine learning and get into programming using a high school level knowledge of math. Yes, it's totally possible.
All right, it looks like that's all the questions we have. Again, thank you, Sebastian, so much for your wonderful presentation and thoughtful answers. And to our audience, keep an eye out for our newsletter. And again, the recording of this event will be available online soon. Thank you all for attending.
Thank you so much.
Thank you.